Cessna 241, 4 miles north of Wasson.
Turn left, heading 140. Maintain 6,000 until established on the localizer.
Cleared for ILS, runway 11 left approach. Contact tower at the outer marker, 118.3.
241 left to 140. Maintain 6,000. Cleared approach 11.
This is a typical exchange of information between a pilot and a controller. But whether you've flown many approaches in actual conditions or are just beginning your instrument training, you may have questions about the criteria that determine how an approach must be flown. For example, why do some approaches have different minimums, even though they are based on the same nav aid? How much obstacle clearance is provided on the final approach segment? Why don't some approaches have a final approach fix, while others do? And what is the significance of a final approach fix? And what do you need to see in order to descend below the minimum descent altitude or decision height? In this program, we'll answer these questions and many more by concentrating on the procedures, regulations, and criteria for flight from the final approach fix inbound. The reference for instrument approaches in the United States and many other countries is an FAA publication called the United States Standard for Terminal Instrument Procedures, abbreviated TIRPS. This publication standardizes the terminology and establishes specific criteria for each type of approach. A different document called the Procedures for Air Navigation Services, Aircraft Operations, or PANSOPS, is used for approaches created under the guidelines of the International Civil Aviation Organization. For this program, we'll concentrate on those approaches created using the TIRPS criteria. Specific approach procedures are designed by the governing authority in each country. In the United States, this is the Federal Aviation Administration. The FAA provides source material for each approach to chart suppliers, such as Jeppesen-Sanderson. The chart suppliers take this information and convert it into an easily readable format. To begin our discussion, let's look at what a final approach fix is and what purpose it serves. A final approach fix is the point on the procedure where the final approach to an airport can be initiated. It also identifies the beginning of the final approach segment. This segment extends to the missed approach point or the runway, whichever is encountered last. On Jeppesen charts, the final approach fix, or FAF, is identified in the profile view by the Maltese cross for non-precision approaches and by the glide slope intercept point at the minimum glide slope intercept altitude for precision approaches. Each segment of an approach is designed to provide adequate obstacle clearance. For example, on the initial approach segment, you have 1,000 feet of obstacle clearance when you're flying at the prescribed altitude. This obstacle clearance extends 4 nautical miles on either side of the charted course. The width of the intermediate segment, on the other hand, tapers from 4 nautical miles on either side of the course at the start of the segment to as little as 2 nautical miles at the start of the final approach segment. The intermediate segment provides you with a minimum of 500 feet of obstacle clearance. For the final approach segment, however, the type of approach dictates the protected airspace and the obstacle clearance. For example, let's look at the protected airspace for a straight-in landing VOR approach with a final approach fix. The boundaries of the protected airspace are defined by a trapezoid that is made up of primary and secondary areas. The center, or primary area, is 2 miles wide at the VOR and expands uniformly to 5 miles wide, 30 miles from the facility. The secondary area is on either side of the primary area. It is 0 miles wide at the VOR and expands uniformly to 1 mile on each side of the primary area at the 30-mile point. Within the primary area, the minimum descent altitude assures you of at least 250 feet of obstacle clearance. In the secondary area, this clearance decreases from 250 feet at the inner edge to 0 feet at its outer border. Outside the secondary area, you may not have obstacle clearance even if you're at the prescribed altitude. The actual protected airspace, however, only applies to the area between the final approach fix and the missed approach or the runway, whichever is encountered last. If the approach is toward the VOR, the protected airspace decreases in width as you near the airport. On the other hand, if the approach is away from the NavAid, the width of the protected airspace increases. You can determine the width of the protected airspace at any point from the NavAid on this approach by using a simple formula. 1/2 the width of the primary area is equal to the distance from the VOR times 0.05 plus 1. You can find the width of the secondary area by taking the distance from the NavAid times 0.0333. Let's see how this works. Suppose you are located 10 nautical miles from the facility. You can find 1/2 the primary area by taking the 10-mile distance times 0.05, then adding 1. In this case, 1/2 the width of the primary area is 1.5 nautical miles. The total width of the primary area is 3 nautical miles. Remember, you also have some obstacle clearance, but in a decreasing amount in the secondary area. As you can see, by taking the distance of 10 miles times 0.0333, your protection in the secondary area at this point is 1/3 of a mile. Therefore, as long as you remain within approximately 1.8 miles from the prescribed center line, you will have some guarantee of obstacle clearance. Remember, though, that the obstacle clearance for this approach is 250 feet within the primary area, but tapers to 0 at the outer edge of the secondary area. To illustrate this point, suppose you drifted 1.75 miles from the center line. In this case, you could possibly have only 62 feet of obstacle clearance. This might seem like plenty of airspace, but how many times have you gotten into an aircraft and discovered that the altimeter is not reading the field elevation even with the correct altimeter setting? If the error in this case was over 60 feet, you might not clear the obstacle. So to ensure the maximum amount of obstacle clearance, you should always maintain the approach center line and don't descend below the published altitude. There is a similar formula for each type of approach, but rather than show each one, we've included them at the end of the video presentation. Now let's look at another kind of approach where the VOR does not have a final approach fix. In this situation, the facility is usually located on the airport, and you shoot the approach by flying to the facility and then executing a procedure turn before entering the final segment. Because there is no final approach fix, the obstacle clearance is raised to 300 feet for the primary area, with the secondary area starting at 300 at the inner area and tapering to 0 at the outer edge. The protected airspace for this approach is 10 miles long and longitudinally centered on the final approach course. This relates to the 10-mile limit on most procedure turns. The primary area is 2 miles wide at the facility, just like the VOR approach with an FAF, but it expands at a greater rate. In fact, it is 6 miles wide at the 10-mile point, compared to a 3-mile width on the other approach. The secondary area is 0 miles wide at the facility and extends to 1.34 miles on either side of the primary area at the 10-mile point. Another type of approach which has a 300-foot obstacle clearance is the NDB with a final approach fix. Here, the final approach fix provides for better runway alignment. But an NDB approach is not as accurate as a VOR approach. The protected airspace for this approach extends 15 nautical miles from the NAVAID compared to 30 miles for the VOR approach with a final approach fix. The primary protected area is 2.5 miles wide at the non-directional beacon and expands uniformly to 5 miles at the 15-mile point. The secondary area expands from 0 at the facility to 1 nautical mile on either side of the primary area, 15 miles from the NAVAID. Like the VOR with a final approach fix, this procedure can be established toward the NDB or away from the facility. If the NDB does not have a final approach fix, the obstacle clearance within the primary area increases to 350 feet, while the secondary area tapers from 350 feet at the inner edge to 0 at the outer edge. Since this type of approach usually requires a procedure turn, the protected airspace is very similar to that of the VOR approach without a final approach fix. With this approach, however, the width at the facility is 2.5 miles instead of 2, but still expands to a 6-mile width 10 miles from the NDB. The secondary area starts at 0 and expands to 1.34 miles on either side of the primary area. Now let's look at how the minimum descent altitude, or MDA, for a specific approach is affected by the obstacle clearance requirements. In designing an approach, the FAA determines the controlling obstacle, then applies the required obstacle clearance, or ROC. As an example, suppose the FAA is creating a VOR approach with a final approach fix to Bayfield Municipal Airport. They have determined that the MSL altitude at the top of the controlling obstacle is 1,260 feet. As we already know, the required obstacle clearance for this type of approach is 250 feet. By adding the altitude of the controlling obstacle and the 250-foot required obstacle clearance, the MDA can be determined for this approach. In this case, it would be 1,510 feet. Since MDAs are rounded up to the nearest 20 feet, the actual MDA would be 1,520 feet. Of course, an MDA can be increased for a number of reasons. This can occur when the approach is located in areas of precipitous terrain, when you must get your altimeter setting from a remote site, when the length of the final approach is excessive, or when the minimum descent altitude does not allow for the proper obstacle gradient during the missed approach. In the case of a remote altimeter site, the required obstacle clearance must be increased 5 feet for each mile, in excess of 5 miles, that the remote site is from the airport. If the final approach fix is located farther than 6 nautical miles from the landing surface, the obstacle clearance must be increased 5 feet for every 1/10 of a mile beyond the 6 miles. Going back to our approach at Bayfield, suppose you must obtain your altimeter setting at a site 50 miles away, and the final approach fix is located 7.5 miles from the landing surface. To determine how much altitude must be added to the MDA, find the number of miles from the airport to the remote altimeter site. In this example, it is 50 miles. However, for this calculation, only those miles over 5 miles are used. 50 minus 5 equals 45. Then take this value times 5 feet. The result is a 225-foot increase. Since the final approach is 1.5 miles beyond the 6-mile point, we must increase the obstacle clearance by 5 feet for every 1/10 of a mile beyond 6. In this example, there are 15 tenths. 15 times 5 equals a 75-foot increase. Let's review the elements involved. When the controlling obstacle is added to the required obstacle clearance, the remote altimeter sight adjustment, and the adjustment for the final approach length, the MDA for this approach to Bayfield becomes 1,810 feet. Again, this value must be rounded up to the nearest 20 feet. As a result, the MDA, which would appear on the source material and later be converted to an approach chart, would be 1,820 feet. Now that we've discussed how the MDA is determined, let's look at some practical aspects of flying the final approach. When making your descent from the final approach fix to the MDA, there are some things which you should consider. Among these are, how fast should you descend? Descending as rapidly as possible may not be the best approach technique. Descending too rapidly may result in shooting through the MDA before the sink rate is arrested. At the same time, the descent should be sufficient to assure reaching the MDA prior to the missed approach point. The best plan is to descend at a rate that allows you to reach the MDA smoothly, with time to set up for a straight-in or a circle-to-land maneuver. If you reach the MDA and you're still in IFR conditions, stay there. Don't try to ease it on down a few more feet hoping you'll break out. The MDA is established and carefully flight checked for obstacle clearance. It's safe only as long as you maintain it. Some final approach segments may contain a step-down fix for obstacle clearance purposes. Where a step-down fix is established, you can descend to a lower altitude after you have safely overflown the controlling obstacle as long as you can identify the fix. If not, you must fly at the higher MDA. When you reach the missed approach point, you have two options. Land if you have visual contact, or immediately begin the missed approach. You cannot descend below the MDA on a non-precision approach or below the DH on a precision approach unless you are continuously in a position from which a descent to a landing on the intended runway can be made at a normal rate of descent using normal maneuvers. In addition, the flight visibility cannot be less than that prescribed for the procedure being used. You must also be able to clearly see and identify one of the following: the approach light system, the threshold or its markings or lights, runway end identifier lights, VASI lights, the touchdown zone or its markings or lights, or the runway or its markings or lights. If you use the approach lights as a visual reference, you must not descend below 100 feet above the touchdown zone elevation unless the red terminating bars or the red side row bars are also distinctly visible. If these visual cues are lost at any time after the descent below the MDA or DH, you must immediately execute a missed approach. To help you make the transition from the instrument portion of an approach to the visual portion, some non-precision procedures have a visual descent point or VDP. This point is identified on approach charts with the letter V. Note that a VDP is not a visual reference to the terrain, but a fix derived by instruments, usually by DME on VOR and localizer approaches. When you reach the VDP, you may begin a descent from the MDA to the runway touchdown point, provided you can clearly see and identify one of the visual references discussed earlier. If a VASI is installed, the VDP is the point where the lowest VASI glide slope intersects the lowest MDA. Where VASI is not installed, the VDP is normally located at the point on the final approach course at the MDA, where a descent gradient of 300 to 400 feet per nautical mile will intersect the threshold. This descent gradient approximates a 3-degree glide slope. When flying an approach which includes a visual descent point, maintain the MDA until reaching the VDP. If you cannot receive the VDP, fly the approach as though no visual descent point existed. Now let's examine the circle to land maneuver. Because it's often conducted at low altitudes within a limited area, and often at night or in marginal weather conditions, a circling maneuver can be considerably more complicated than the straight-in landing, even though the MDA is higher. The protected airspace for this maneuver depends on the category of your aircraft. These categories are based on approach speeds determined by taking the stall speed of the aircraft in the landing configuration at maximum landing weight times 1.3. The higher the approach speed, the greater the protected airspace. For example, the protected airspace for a Category A aircraft is an area composed of arcs measured 1.3 nautical miles from the end of each usable runway. It also includes the tangent areas. The protected airspace for Category B aircraft extends out to 1.5 nautical miles. Category C extends out to 1.7 miles, while Category D arcs extend to 2.3 nautical miles from the end of each usable runway. The obstacle clearance within these areas is 300 feet. As the aircraft approach speed increases, the minimums normally increase. Therefore, if you're flying the maneuver at an indicated airspeed faster than the speed range for your category of aircraft, use the minimums for the next higher speed range. You can select from a number of different patterns when flying a circling approach. This pattern is recommended if your final approach course intersects the runway center line at less than 90 degrees and you sight the runway in time. If you see the runway too late, you can use this type of pattern. If you want to land in the opposite direction from the final approach and the runway is sighted in time for a turn to the downwind leg, use this pattern. If the runway is not visible in time for a turn to downwind, you can overfly the airport and then circle to establish a downwind leg. But no matter what pattern you use, you should try to maneuver in the shortest amount of space to the appropriate base or downwind leg. Since other flights might be in progress at the airport, you should also maintain a constant awareness of the activities around you. At airports without a control tower, it may be desirable to fly over the airport to observe the wind and pattern indicators and other traffic which may be on the runway or flying in the traffic pattern. Due to the additional maneuvering required for this type of approach, you may encounter some restrictions. In some cases, the procedure is not authorized at night. At other times, the circling maneuver might be prohibited in certain sectors. For example, here the maneuver is not authorized northeast of the airport between the extended center lines of runways 1533 and 826. Checking for these restrictions is an important part of your pre-flight planning. During a circling maneuver, you must maintain at least the circling MDA until you reach a point where your aircraft is continuously in a position from which a normal descent to a landing on the intended runway can be made at a normal rate of descent using normal maneuvers. Remember, the obstacle clearance may only be 300 feet. If you are at or above the MDA and you lose sight of the identifiable part of the airport, unless it occurs only because of the bank of the aircraft, you are to immediately execute a missed approach. When you begin a missed approach from a circling maneuver, make your initial turn toward the landing runway. Remember, the airspace over the airport affords you the greatest obstacle clearance protection. Now let's take a look at the criteria used during a precision approach, specifically a Category 1 ILS. The protected area of a Category 1 final approach extends outward 50,000 feet from a point beginning 200 feet from the runway threshold. However, only that portion which is between the 200-foot point and glide slope interception is used. Except where an offset localizer is used, the width of this segment is 500 feet on either side of the extended runway centerline, starting at the 200-foot point. It expands uniformly to 8,000 feet on either side at a point 50,200 feet from the threshold. Obstacle clearance for a Category 1 ILS is based on a final approach obstacle clearance surface, which is broken into two sections. The intersection extends outward for 10,000 feet from the 200-foot point. This section is further divided into two zones. The first zone begins at the 200-foot point and at the runway threshold height. It extends to the middle marker or the decision height, whichever is farther. For a 3-degree glide slope, the slope of this obstacle surface is 34 to 1. This means that for every 34 feet outward, the obstacle surface increases 1 foot in height. The obstacle clearance surface for the second zone starts at the middle marker and is an extension of a line beginning at the runway threshold height 975 feet from the point where the glide slope intercepts the ground. It extends outward from this point for 10,000 feet. The slope of this line is also 34 to 1. Beyond 10,000 feet, the slope of the outer section increases to 29.5 to 1. In comparison, a 3-degree glide slope is 19 to 1. The distance between the glide slope and the obstacle surface is the required obstacle clearance. The formulas for determining the protected airspace and obstacle clearance at any point along the approach are given at the end of this presentation. But you should remember that as you get closer to the airport, the amount of protected airspace and obstacle clearance decreases. For example, on this approach, the protected airspace at the outer marker is 5,300 feet on either side of the runway centerline. The required obstacle clearance is 690 feet. At the missed approach point, the protected area has decreased to only 926 feet, and the obstacle clearance is only 109 feet. So remember, to assure obstacle clearance, stay on the center line and the glide slope. On an ILS approach, there is a transitional surface which is somewhat like the secondary area discussed earlier. This surface is an inclined plane with a slope of 7 to 1. It extends outward and upward from the obstacle surface for a lateral distance of 5,000 feet. The decision height on a Category 1 ILS is normally 200 feet above the touchdown zone elevation. However, the landing minimums usually increase when a required component or visual aid becomes inoperative. For example, if the middle marker is out, the decision height increases by 50 feet. Loss of the glide slope on an ILS approach not only increases the minimums, but changes the procedure from a precision approach to a non-precision approach with an MDA. In this case, the obstacle clearance is 250 feet. On ILS charts provided by Jeppesen, the precision approach is shown with a solid line, and the non-precision approach with a dotted line. So far in this program, we've looked at standard non-precision and precision approaches. At major air terminals, however, ATC may use special procedures to accommodate the heavy flow of air traffic. While most of these procedures will not change the way you fly the final approach, you should be aware of their unique characteristics. All of the procedures we'll look at here use the ILS approach. But instead of a single approach, ATC can land aircraft on different runways using simultaneous, parallel, and converging ILSs. They can also have you perform an approach to one runway and then have you sidestep to another runway. Simultaneous ILS approaches may be used at airports with parallel runways with at least 4,300 feet between center lines. A simultaneous approach provides both vertical and lateral separation prior to glide slope intercept. After intercept, however, only lateral separation is provided. A no-transgression zone at least 2,000 feet wide is established between the extended runway center lines for lateral separation. If you deviate into the no-transgression zone, the controller will provide corrective instructions. If you fail to follow the instructions, the controller will instruct the pilot on the adjacent localizer to alter course if necessary. In contrast, parallel ILS approach procedures may be used with only 2,500 feet between the center lines. However, with these approaches, the aircraft are staggered. This provides a minimum of 2 nautical miles radar separation between successive aircraft on adjacent localizer courses and a minimum of 3 miles radar separation from aircraft on the same localizer course. Another type of approach you might encounter is the simultaneous converging ILS approach. In this case, ATC may conduct instrument approaches to 2 different runways having angles from 15 to 100 degrees apart, but only at airports which have been approved for such procedures. In order for these types of approaches to be approved, each runway must have its own separate ILS or MLS instrument approach procedure with non-overlapping final approaches. In addition, the missed approach points must be 3 miles apart. And the missed approach procedures must ensure that the missed approach protected airspaces do not overlap. When simultaneous converging approaches are in progress, you will be informed by the controller as soon as feasible after initial contact or through ATIS. When parallel runways are separated by 1,200 feet or less, ATC can authorize a sidestep procedure whereby you fly the approach to one of the runways, followed by a straight-in landing on the adjacent runway. You are expected to start the sidestep maneuver as soon as practical after you have the runway in sight. Sidestep maneuvers require higher minimums than a straight-in landing, but are normally lower than circling minimums. Before we end, let's briefly talk about the missed approach. When executing a missed approach, safe obstacle clearance is assured only when you fly the established missed approach procedure. The protected obstacle clearance areas for the missed approach are based on the assumption you will initiate the missed approach at the missed approach point at a height no lower than the MDA or DH. Reasonable buffers are provided for routine maneuvers, but no consideration is given to an abnormally early turn. Here are some techniques that might make a missed approach easier. Number 1 is to know the missed approach procedure before you start the approach and be prepared to execute it. If you have dual radios, and for IFR you certainly should, set up the missed approach frequency and radio on one of them as soon as it is no longer needed for the approach procedure in progress. This technique is especially helpful when the missed approach procedure uses a nav aid other than the one used for the approach. During a climbing turn on the gauges, you should not be tuning the radios. In addition, ATC communications are important, but don't worry about reporting the missed approach until everything is well under control. It's very satisfying to make an instrument flight that ends in a perfect approach after you break out at the MDA or DH right on the runway center line. It doesn't happen by chance. current proficiency, careful planning, maintaining prescribed altitudes and center lines, and a professional attitude are all prerequisites for such a flight.